Hello, welcome to another module in this massive open online course. So, we are looking at positive semi-definite and positive definite matrices. So, let us continue our discussion. So, in fact, let us look at an example. Let us look at a simple example for a PSD matrix. Consider the matrix A, which is equal to 1, 3. This is our 2 cross 2 matrix A. Let us try to see, is this positive definite or positive semi-definite. So, is this PSD or is this PD? Of course, you might recall PSD essentially means positive semi-definite, and PD is positive definite. So, this is either positive semi-definite or this is positive definite. All right. So, to do that, let us follow the first principles. Let us look at x bar transpose A x bar for any vector x bar. Okay. So, this is a real matrix clearly. So, we can look at x bar transpose A x bar, and this is equal to x1. Of course, the vector x has to be 2 dimensional since A is 2 cross 2 matrix, 1, 3, 3, 9 where times x bar. So, this is your x bar transpose. So, this is x bar transpose, this is the matrix A, this is the matrix x bar. This is equal to I can write this as follows. So, first multiply the row on the left by the matrix A. So, this will give me x1 plus 3x2 and then you have 3x1 plus 9x2 times x1 x2, and that gives us, if you continue with this, that gives us x1 square plus 3x1 x2 plus 3x1 x2 plus 9 x2 square, which is equal to, you can easily x1 plus 3x2 whole square, which is greater than or equal to 0. In fact, this can also be equal to 0 if x1 equals minus x1 plus 3x2 equal to 0, or x1 equal to minus 3x2. So, this is only greater than or equal to 0. This is not always greater than 0. In fact, it can be equal to 0 if x1 equal to minus 3x2. Therefore, this is only positive semi-definite, not positive definite, right. So, in fact, since this is only greater than or equal to 0, this matrix A equals 1, 3, 3, 9, this is PSD, not PD, since this can be equal to 0 whenever we have a vector x bar such that x1 equal to minus 3 x2. So, A is in fact a positive semi definite matrix. Let us continue this example 5 further. What about the eigenvalues of A? What about the eigenvalues of A? So, to find the eigenvalues, remember we have to find A minus lambda I, set the determinant equal to 0. You have to set the determinant equal to 0. This is 1, 3, 3, 9 minus lambda times, of course, you have to take the 2 cross 2 identity matrix, this equal to 0. This implies that you have 1 minus lambda, 3, 9 minus lambda, the determinant of this must be equal to 0. This implies that 1 minus lambda into 9 minus lambda minus 3 into 3 9 equal to 0, which implies 9 minus 9 lambda minus 10 lambda plus lambda square minus 9 equal to 0, which implies lambda square. So, you can see the 9's go away. So, you have lambda square minus 10 lambda equal to 0, which essentially implies lambda square equal to 10 lambda, which implies lambda equal to either 0 or 10. And in fact, now you can see one of the eigenvalues is 0, right? One of the eigenvalues is 0. Eigenvalues is also, one of the eigenvalues is 0. That is, eigenvalues are not greater than 0, but eigenvalues are greater than or equal to 0. Hence, this can only be a positive semi definite matrix, right. So, first interesting thing, both eigenvalues are real. Both eigenvalues are real. One of the eigenvalues equal to 0 implies once again that this can only be a positive semi definite matrix. In fact, you can see lambda I eigenvalues are greater than or equal to 0, alright. Both eigenvalues are real, both are greater than or equal to 0. Both eigenvalues are in fact greater than or equal to 0. That is what we expect of a positive semi definite matrix. Eigenvalues or positive definite matrix eigenvalues have to be greater than 0. Positive semi definite matrix eigenvalues have to be greater than or equal to 0. In fact, in this case one of the eigenvalues is 0. So, this is only a positive semi definite matrix. So, let us now find the eigenvectors of this matrix and let us check the property about the eigenvectors. I hope all of you remember the property about the, of course, the way to find the eigenvectors is eigenvectors lie in the null space of A minus lambda I. I hope all of you remember this. Eigenvectors lie in the null space of A minus lambda I. What is A? You have A equals 1, 3, 3, 9, take lambda equal to 10, A minus lambda I equals 1 minus 10, that is minus 9, 3, 3, 9 minus 10, that is 1. So, we have A minus lambda I, we have to find the vector x bar in the null space of this. So, A minus lambda I times x bar equal to 0. This implies minus 9, 3, 3, 1 times x1 x2 equal to 0, which implies, you can see there is redundancy in this. So, we can only solve one equation. So, 3x1 plus x2 equal to 0, we are solving the second equation. You can solve the first equation, you will get the same. In fact, if we write the first equation, let us write that, I mean, to avoid any confusion, minus 9x1 plus 3x2 equal to 0, 3x1 plus x2 equal to 0, both give minus 9x1, I am sorry, this has to be minus 1, I guess. So, a minus lambda, this has to be minus 1, right. So, this has to be 9 minus 10, which is minus 1, both. So, 3x1 minus x2 equal to 0, both give x2 equal to 3x1. This is the property the eigenvector has to satisfy. So, if you set x2 equal to 1, x2 or x2 equal to, or x1 equal to 1, this implies x2 equal to 3. So, you have a free parameter, that is x1, and you can, and that naturally is the case because the eigenvector is invariant on scaling, right. So, you can scale the eigenvector by any constant and it will still remain an eigenvector, and that is exactly reflected here, where you can see there is a free parameter. You can choose x1, x2 gets determined automatically. Okay. So, the eigenvector x bar equal to, what will the eigenvector be, x1 equal to 1. Now, the unit norm eigenvector, I can call this as the eigenvector. Now, the corresponding unit norm eigenvector, I have to divide it by the, I have to divide this by the, norm. Okay. So, the unit norm u1 bar, let us call this as x1 bar, u1 bar equals x bar, x1 bar divided by norm x1 bar, which is equal to 1 over square root of 10 1 comma 3. Now, similarly, if you look at a minus lambda I corresponding to lambda equal to 0, this will simply be a. Now, to find the eigenvector corresponding to lambda equal to 0, basically we have to find the null space, find a x bar equal to 0, that is vector in null space of a, since lambda equal to 0. This gives eigenvector corresponding to lambda equal to 0, and this you can find as follows. You have 1339 times x1 x2 equal to 0, this implies x1 plus 3x2 equal to 0. You can solve again the same thing as the previous case. You can solve the second equation, it will give you the same thing, which implies x1 equals minus 3x2. There is again a free parameter in this case. You can say x2 is a free parameter or x1 is the free parameter, whatever it is. So, if you set 1, it determines the other. So, x1, so if you set x2 equal to 1, x1 will be equal to minus 3. So, that is, we can call this as, or x2 bar, this is the eigenvector. In fact, this is also the vector, this is also a basis for the null space of the matrix A. You can say this also corresponds to an eigenvector of the matrix, this eigenvector of the matrix A corresponding to the eigenvalue 0, okay, which is essentially the same thing as saying A x bar equals 0 times x bar, which is 0, and that essentially says that x bar is in the null space of A, right. So, I hope that is also clear. So, A x bar, if you look at A x bar equal to lambda times x bar equal to 0 into x bar equal to 0 if lambda equal to 0, which means x bar eigenvector for which is x bar, which is the eigenvector for lambda equal to 0 lies in null space of A. Okay, so it's a straightforward result. I mean, it's not very difficult to see. And now, if you look at A equal to 1 3 3 9, and if you set out to find Ax, solve Ax bar equal to 0, this implies 1 3 3 9 x1 into x2 equal to 0, and this implies, if you look at this, x1 plus 3x2 equal to 0, which implies x1 equals minus 3 x2. Okay, I think this is essentially what we have already found, right. So, this is the eigenvector corresponding, and x2 bar equal to, essentially that is what we had. So, then the eigenvector is corresponding to this is x2 bar equal to minus 3 comma 1. So, we have x2 bar equals minus 3 1, and we have u2 bar, which is x2 bar divided by norm x2 bar, and this is 1 over square root of 10 minus 3 comma 1. Okay. Now, let us look at these two eigenvectors, u1 bar equals to unit norm eigenvectors, u1 bar equal to 1 over square root of 10. We have, I guess, 1 3, and u2 bar equal to 1 over square root of 10 minus 3 1. It is not very difficult to see that u1 bar transpose u2 bar equals 1 over square root of 10 1 3 into 1 over square root of 10 minus 3 1, and this is nothing but 1 over 10 into 1 into minus 3 plus 3, which is equal to essentially 0. Therefore, what you can see very easily is that u1 bar transpose u2 bar equal to 0, which is again verifies the property that the eigenvectors corresponding to distinct eigenvalues of the positive semi-definite matrix in this case lambda equal to 0 comma 10 of the PSD matrix are orthogonal, that is eigenvalues, eigenvectors corresponding to the distinct eigenvectors, right. That is u1 bar equal to 1 over square root of 10 1 comma 3, and u2 bar equal to 1 over square root of 10 minus 3 comma 1, these are orthogonal. And now, we form the matrix of these unit norm eigenvectors. So, we have unit norm orthogonal eigenvectors, we have u equals 1 over square root of 10, that will be 1 3 minus 3 1, and the diagonal matrix of eigenvalues in this case is lambda, which is equal to, it is not very difficult to see, 10 0. This is the diagonal matrix of eigenvalues. This is the diagonal matrix. This is the diagonal matrix of eigenvalues. In fact, you can see is a unitary matrix u transpose equal to u transpose u equals identity. This u can see contains orthonormal column. So, this is a unitary and therefore, A you can clearly see can be written as u lambda u transpose, which is 1 over square root of 10 1 comma 3 minus 3 comma 1 times lambda, which is essentially 10 0 0 0 times u transpose, which is 1 over 10 1 comma 3 minus 3 comma 1, and if you multiply this, you can see you will get back A, which is 1 comma 3. So, this is basically the eigenvalue decomposition. So, this is the eigenvalue decomposition of the PSD matrix, that is essentially u sigma u transpose, that is the eigenvalue decomposition of the PSD matrix A. So, although this is a very simple example, it is a simple 2x2 example, illustrates several interesting points. Essentially, how do you find the eigenvalues of the PSD matrix, and from that you find that one of the eigenvalues is 0. So, in fact, this is a positive semi-definite matrix. Then you find the eigenvectors, then you find the unit norm eigenvectors. In fact, you realize that the eigenvectors are orthogonal, right, because these are the eigenvectors corresponding to a PSD matrix for distinct eigenvalues. The eigenvalues are also greater than or equal to 0, they are real and greater than equal to 0, and finally, once you construct the unitary matrix U corresponding comprising of the orthonormal, that is unit norm and orthogonal eigenvectors as its columns, then you will realize that U is a unitary matrix. So, U transpose U is identity, and the diagram and the eigenvalue decomposition is in fact given as U lambda U transpose. See, normally for a normal square matrix it is given as U lambda U inverse, but for the positive symmetric semi-definite matrix it is given as U lambda U transpose, because U transpose itself is U inverse. In fact, in this case it is given as U times lambda times U transpose, where lambda is the diagonal matrix comprising of the eigenvalues. First one is lambda 1 0, lambda 1 is 10, and the next one lambda 2 equals 0. Alright, so the diagonal matrix will be the lambda is a diagonal matrix with the diagonal elements given as 10 0. Okay. So, it is a very interesting example, very simple but very interesting, clarifies a lot of. So, the simple examples as they are clarify a lot of interesting ideas and clarify, they illustrate very clearly several ideas. Now, let us look at another interesting application. Remember, I told you positive semi-definite matrices arise very frequently in linear algebra random vectors. Why is that the case? And for that you have to look at again the covariance matrix, that is let us consider a zero mean random vector. With covariance, this R we know is called or is termed the covariance matrix. R is termed the covariance matrix, and sorry, this has to be expected value of Z bar transpose. Now, turns out that R is always, the covariance matrix is always a positive semi-definite matrix. Covariance matrix is always a positive semi-definite matrix, that is R is always, any covariance matrix is always PSD. How, why is that? Now let us take any vector z bar, let us perform z bar transpose R into z bar, this will be, I am sorry, let us perform x bar transpose R into x bar, this is equal to x bar transpose, expected value of R is expected value of z bar transpose times x bar. Now take the x bar inside, this is expected value of x bar transpose z bar x bar, which is equal to expected value of x bar transpose z bar whole square. And now this is the expected value of x bar transpose z bar whole square, which is a non-negative quantity, therefore this is always greater than or equal to 0, right. So which implies expected, so this implies x bar transpose R, x bar is always greater than or equal to 0 for all x bar. This implies by definition R has to be a PSD matrix. R has to, because x bar transpose R, x bar is always greater than or equal to 0, it being expected value of x bar transpose z bar whole square. Okay. Therefore, any covariance matrix is always a positive semi-definite matrix, and this has very interesting applications. So first of all, it is a symmetric matrix, so we have R equal to R transpose. Secondly, if you look at this, R can be decomposed, because it is a positive semi-definite matrix, R can be decomposed as R tilde transpose. Remember we saw this is the Cholesky decomposition, right. R can be decomposed as R tilde transpose, right, because it is a positive semi-definite matrix. Now let us look at what happens to R tilde inverse z bar. Let us call that as z tilde equals R tilde inverse z bar. Then we have of z tilde transpose is expected value of R tilde inverse z bar transpose R tilde, which is, now if you take R tilde outside, this is R tilde inverse expected value of z bar transpose R tilde. I am sorry, this has to be R tilde inverse transpose, which I am going to write at R tilde minus t. So R tilde minus t. So note R tilde inverse transpose is what I am writing, and what is frequently also written as R tilde minus t. And now this is equal to R tilde inverse expected value of z bar transpose, this is R tilde minus t, which is nothing but R tilde inverse into R is R tilde transpose into R tilde minus t. And now you can see this R tilde inverse into R tilde, this is identity, R tilde transpose R tilde inverse transpose is identity. So this is essentially equal to identity. So expected value of z tilde transpose equals identity, which means z tilde contains uncorrelated components, which is, remember we said whenever the covariance matrix is identity, the components are uncorrelated, because off diagonal elements are 0. So components are uncorrelated, in fact unit variance, right. In fact they are also unit variance, if you see the diagonal elements are 1, in fact also unit variance. And in fact if Z is Gaussian, if Z bar is multivariate Gaussian, this implies Z tilde is Gaussian, and for Gaussian uncorrelated implies independent Gaussian and IID 0 mean contains IID 0 mean, unit variance contains IID 0 mean, unit variance components, contains IID 0 mean unit variance components, because Z tilde, the covariance matrix is identity. So, the components are uncorrelated, which for the case of Gaussian also means that they are independent, and of course, since the diagonal elements are 1, it means the variance of each component or each element of this vector Z tilde, that is equal to 1. The other way around, now if you want to generate, how to generate multivariate Gaussian, this process is an interesting name. So, this process is termed as whitening, right. So, this process where you have Z tilde equal to R inverse Z, this is termed as whitening. This is termed as whitening. Why is this termed as whitening? Because it results in white or uncorrelated components, right, because Z tilde contains uncorrelated components. So, if you go back to that your knowledge of random processes, right, when you have a random process in which the different samples are uncorrelated, there is autocorrelation is the impulse function. If you look at the power spectral density, it becomes flat, right, and we call that as basically a white random process. So, similarly you have essentially, because the covariance matrix is identity, this is a white, I can think of this as a white random vector or white noise, and therefore, this process, that is R tilde inverse into Z bar, which results in this white random vector, right, white noise random vector, this is termed as a whitening filter, or this process is termed as whitening. Okay. So, Z tilde equals R tilde inverse into Z inverse, this Z tilde is a white noise random vector, and this process, this can be termed as a whitening. This is termed as whitening, and in fact, this R tilde inverse, this is termed as the whitening filter. This process R tilde inverse, this is termed as a whitening filter. Now, how to generate Gaussian or multivariate Gaussian with given arbitrary covariance matrix. So, we have looked at the whitening. Now, the analog of that, in fact, you can think of it as the inverse problem, that is, given a noise process, colored noise process Z bar with covariance matrix R, we have produced a white noise process. Now, the question is the other way around, given a white noise, because in most simulators you can generate very easily Gaussian samples which are independent and unit variance, all right. For instance, even MATLAB, the standard function rand n, right, that gives you Gaussian random variables with mean 0, unit variance. Now, if you construct a vector, how do you generate a vector with a given arbitrary covariance matrix? And that is again very simple. Consider Z tilde to be Gaussian zero mean covariance equals identity, that is expected value of z tilde transpose equals identity, right, because most simulators will give you independent identically distributed Gaussian samples of mean 0 and variance 1, right. So, essentially z tilde comprises of IID Gaussian samples, mean equal to 0, variance equal to unity. Now, how do you generate z bar with given covariance R? Very simple, consider z bar equal to R tilde z tilde, and now if you look at expected value of z bar transpose equal to R tilde, this becomes equal to R tilde expected value of R tilde z tilde transpose R tilde, this equals R tilde expected value of z tilde transpose R tilde transpose, this is equal to R tilde expected value of z tilde transpose identity. So, this is R tilde. So, this becomes equal to R tilde transpose, which is equal to R, right. So, now given a Gaussian random vector z tilde which contains IID components mean 0, variance unity, you are now generating a Gaussian random vector z bar 0 mean and arbitrary covariance. So, this is a colored noise. So, from colored noise you can come to white noise, from white noise you can go to colored noise, and that the properties of the positive semi definite covariance matrix, that is R which can be decomposed as R tilde into R tilde transpose, that plays a very important role here, and this is in fact plays a very important role in entire signal processing. So, it allows you to go from colored noise to white noise, from white noise allows you to generate colored noise. Okay. So, therefore, expected value of z bar transpose equal to R, and so that basically you have now colored the noise. So, from z tilde comprising of white noise one can obtain colored noise z bar with arbitrary covariance R. So, from z tilde comprising of white noise one can obtain colored noise z bar with arbitrary covariance matrix, that is R. So, these are essentially the way various interesting. So, we looked at a simple example and we looked at a very interesting practical application of the properties of positive semi definite matrices. As I already told you, positive semi definite matrices arise very frequently because these are the covariance matrices of multivariate probability density functions, and these are the covariance matrices as well as sample covariance matrices. That is, when you evaluate the estimates of these covariance matrices, naturally any estimate of a covariance matrix also has to be positive semi definite, right. So, the covariance matrices as well as the estimates of these covariance matrices are positive semi definite. They have many interesting properties. We have seen that eigenvalues are real, they are greater than or equal to 0, eigenvectors corresponding to distinct eigenvalues, they are orthogonal, and in fact you can have a square root or Cholesky decomposition of these, that is any positive semi definite matrix R or positive definite matrix R can be expressed as R equal to R tilde into R tilde transpose. For a complex matrix it will be R tilde into R tilde Hermitian, alright. So, these are very interesting properties and these arise everywhere in linear algebra, signal processing, machine learning, image processing, these covariance matrices arise everywhere. Wherever you have noise, wherever you have random vectors, positive semi-definite, positive definite matrices arise everywhere. So, this is a very, very important concept. Please go through this again and understand it thoroughly. Thank you very much.